Good afternoon, everyone. I welcome all of you in this session, in the third session of this course. Today, we will be talking about geospatial technology, how it is used for documentation and damage detection of built heritage. I am Dr. Poonam Seth Tiwari, and I'm a scientist here. So today, by now, in these two sessions that you have attended on Monday and Tuesday, you have seen that what is cultural heritage. You must have seen the application of geospatial technology in various other domains, such as in soils, in agriculture, in forestry. But how this geospatial technology can be used for cultural heritage studies. So first of all, let us understand that cultural heritage includes both the physical assets as well as the cultural assets, that is the tangible and non-tangible things. Now, what we are talking about is only the physical asset that our previous generations have left for us, and these are the which we will be talking about is the built heritage. So these are the heritage structures which are one of the most significant elements of cultural heritage, because using these built structures, built heritage, we are able to know a lot many things about the our ancestors. These buildings, these heritage structures, they also reflect about the history, about the lifestyle and tradition of a country and a society. Now, since you must have seen that in India we have a large number of built heritage, built structures, built heritage are there. But these built heritage, they are threatened by various factors. They are under threat by various factors. It can be because of natural hazards. It can be because of earthquake, because of floods, because of any of these things that these built structures can be damaged. Then we can see that a lot of vandalism also happen because of development of cities. So the area of these built heritage is getting encroached and encroached. Okay, and because of the aging problem. Now, when because these structures were constructed thousands of or hundreds of years ago, and over this period of time, these structures become aged, and because of which they are not able to sustain themselves. So proper mapping, damage detection and documentation of these built heritage becomes very, very essential, so that we can preserve and protect these heritage. Now, for all these heritage structures, we don't have any documentation. That means what is the exact structure of the monument, means the architectural drawings that we say. So such type of architectural drawings are not available for these built structures. So that is why this digital documentation of built heritage becomes very, very essential. Then we also need to do the damage detection in these built heritage, because as we have already said that because of the aging problem, lot of damages are happening in these structures. So proper time to time damage detection should be there, so that these damages or cracks or any of these such things can be maintained, can be addressed, and these structures can be maintained, so that these structures will last for a long time. So now, what is the need for digital documentation? As we have already discussed that we require these digital documentation of the monuments, because the architectural drawings are not available. And why should we do it in a digital format? uh, we should employ the recent techniques, as you have seen that lot many surveying techniques, lot many other remote geospatial techniques are there, which are capable of providing multi-dimensional information very easily and quickly also. So, and that too in non-invasive manner. And these techniques, they are they enable effective monitoring and conservation of monuments and heritage sites. Now, if the data is in digital format, then it is easier to store, to analyze, and dissemination of the information is also very easy. The comprehensive documentation of the monument will give us the engineering drawings, photographs, 3D models, historical records, all the ancillary information, everything can be put into one place. So in short, we can say that 3D digital documentation is very effective way of monitoring structures over a period of time. Now, geospatial technology, there are large number of technologies which come under the domain of geospatial technology, which can be used for heritage documentation. As you have seen that new and new sensors and data captured methodologies, the processing technologies, they are coming up. And these newer methods of data capturing, data processing, they have contributed significantly towards the 3D documentation, conservation, and digital visualization of heritage sites. Now, there are various methods of recording and documentation of the heritage sites. They can be the surveying techniques, which you already know, the EDM, total station, GPS. Then we have digital photogrammetry, terrestrial photogrammetry that we have. Then terrestrial laser scanning is also a very good technique, which we will be discussing about in detail. Then we have GPR, ground penetrating radar. If you have looked into the news in the recent past, you must have seen that the survey of a particular mosque in Varanasi is being going on. The scientific survey is being going on. So they are employing this technique only, GPR technique, in which you can know what is underneath a particular structure. So you can have above surface documentation as well as subsurface documentation also. Then you can have space-borne data that we all use. Now, you can also use for higher spatial resolution, you can also use the unmanned aerial vehicle data also. Now, we should focus, or we should be clear that any one technique would not be suitable for documentation, modeling of any of the heritage sites. Why is such? Because all our heritage sites, they are very complex in nature. Some of them are very, means in some heritage sites, some buildings are very tall. There is less space surrounding that particular structure. Some areas, some heritage sites, the buildings have a vast expanse. So any one technique would not be suitable for doing the documentation. So the solution is that we should always go towards the integration of multiple sensors and technologies, so as to get the best of all the technologies. So integration of these technologies, they enable the exploitation of individual technologies and compensate for their limitations also. We can capture the data set at different level of details also, because some people want the data only for visualization, so it can be lower level of detailed data. Then you might require very high resolution data also for certain applications, such as damage detection, for finding out the issues with the paintings and all. So in such cases, then higher level of detailed data set can be utilized. So in short, what we should see, we should focus is that our approach should include multiple sensors, integration of multiple sensors at multi-scale data set should be utilized, so as to get a comprehensive idea about the entire historical site, 3D modeling, geometric detailing, visualization, everything. Now, since last 2 days, you must have seen that how these technologies are used for documentation and damage detection of heritage sites in the Earth observation data, we can have either passive data, active data. Passive includes optical, multispectral, hyperspectral, thermal data. So all of them have some or the other application in this area. Then we have active data set, which is microwave and lidar. Then this was when we are using the Earth observation data. When we are changing the platform, we can have aircraft based data, we can have UAV based data, we can have ground based data. We can also use multi-temporal data for change analysis. Now, in our study, we have used terrestrial laser scanning data. So this data can be used to refine spectral results by including surface morphology information. Either the digital surface model or digital elevation model can be derived from this data. Taking the difference of pre-event correlation and post-event correlation, the areas affected by the damage or change can be identified. So today I'll be talking in detail about some of the work that we have carried out on digital documentation, damage assessment and reconstruction of heritage site. I will be taking the case example of Qutub complex, and within Qutub complex, one or two buildings such as Qutub Minar, and some mosque also. Okay, so similar type of studies are done on different heritage sites, but to show how what are the challenges that we face, how the solutions can be derived, I have taken that case study. So what we will be doing is we will be integrating the multi-source, multi-platform data so as to get an improved 3D documentation of the site. Then we will do the digital blueprinting of the built heritage site, but prior to that we will create architectural primitives also, using which we will create the digital blueprint, and then we will discuss about the damage detection and reconstruction of built heritage. Okay, so this is a procedural workflow that we have followed. So as you can see, we have used terrestrial laser scanning data as well as terrestrial photographs. We also utilized ancillary information from the literature, uh, how these buildings were in and the old maps and so on. Okay, so this is a broad methodology. The terrestrial laser scanner data is processed to generate the 3D point cloud. Similarly, terrestrial photographs are used, and photogrammetric processing is carried out. From here also we generate 3D point cloud. Integration of both the 3D point clouds is done, and using that integrated high resolution dense point cloud, we will extract the architectural primitives and ultimately do a digital blueprinting. The same data set can be used for damage detection and assessment. Once the damage is detected, we can reconstruct the structures virtually also and use it. Okay, so this is the site that we are going to discuss in detail. This is in New Delhi. This is Qutub complex. This particular building is Qutub Minar. Then we have this Alai Darwaza. As you must be aware that there are various buildings within this complex. This is a mosque, Quwwatul Islam Mosque. Then we have Tomb of Imam Zamin. So basically there are various other structures also, but we have worked in detail on these 3 or 4 structures. Okay. So now what we have done is we have for data acquisition, we have developed a workflow, because I will show you what challenges were faced during data acquisition using terrestrial laser scanner and close range photogrammetry. Then we have carried out the data processing, and finally integration of the data was carried out. Okay, so let us start with the Qutub Minar. As you must be aware that Qutub Minar, the height of Qutub Minar is around 72 meters. Okay, now we have this terrestrial laser scanner which we have kept on the ground. So when we have seen that the as you means the same terrestrial laser scanner can capture the data for the top of the tower also, but the point accuracy decreases with the distance because the slant range increases as you take the data for the top of the tower. So if the slant range is increasing, so what happens that the point density decreases. So, and up to a level of 28 meter, 30 meter, we were getting a good point accuracy, point cloud density. So the point cloud density was approximately 4 millimeters at the height of 28 meters. 4 millimeter means that at every 4 millimeter there is a point. Okay, so if there are large number of points, large number of information is there, dense information is there, and so on. But the same point density decreases to 14.24 mm at the top of the tower. That means the between two different points, between 2 points, the distance, average distance is 14 millimeter at the top of the tower. Now 14 millimeter, that means 1.4 or approximately 1.5 centimeter. It is a big distance. So we and within that much distance, lot many features would be we would miss. In the here level in the image number 1, you can see this is when we have integrated all our terrestrial laser scanner scans. You can see for the lower area, for the first ground first level of the minar, we are getting very high point density, but as we move ahead, then the point density decreases. Okay, and naturally the details are lost. You can see the details are lost, and even the textures that we get are not proper. So with such type of data set, we won't be able to complete our objective. So what we okay, anyhow, using one single scan of terrestrial laser scanner, you cannot cover the entire minar also, and there were a lot of complications because of the angular shape and the complex pattern of the minar on the surface. So what because of such shape and patterns, we require a high overlap between the scans. So based on the literature, it was suggested that approximately 90% overlap should be there between two scans. So we did all the calculations mathematically, and we found out that a minimum of 21 scans are required for, using which we can get 90% overlap between these scans. Okay, so you can see this is a footprint of the minar, and all across the all around the minar we have from a distance of 6 meter to 8 meter. The minimum is 6 meter, maximum is 8 meter. Within this periphery, based on the availability of clear space, we have placed our terrestrial laser scanner at specific locations, which we have found using the field planning. So up to the height of 28 to 30 meter, as I have shown you, the TLS point cloud was used. But after beyond this 30 meter, we needed to improve this point cloud, and then we used, okay, this is the processed terrestrial laser scans. You can see this is the total number of scans that we have used is 21. Okay, but still at the bottom we have got very high density. At the top the density was less. You can see here. So to complement that point cloud, we have used close range photogrammetry also. Now close range photogrammetry also means only one type of lens would not be able to give you the best result, because what happens that the near range photographs, they don't cover the full extent of the minar. The far range photographs don't cover major parts of the lower portion because of the obstructions. So we have done some field planning here also, and use two different we have used two different focal length cameras. For near range we have used a lens of 18mm focal length, and for far range we have used the lens of 300mm focal length. So similarly, we have calculated how many number of scans should be required for near range and for far range. So you can see here around 20 scans for far range, and similarly near range also some 14 or so scans were taken. So you can see here 19 near range and 20 far range scans were captured. These are the position of scans. This is the minar, and at the periphery these are the photographs from where these photographs were captured. Now on the other side I have shown you the photographs. The photogrammetric of these near range and far range photographs was carried out, and the 3D point cloud was generated using these also, far range, near range, and we have integrated the TLS scan also along with that, and got a complete integrated 3D point cloud for Qutub Minar, in which the point density was quite good throughout the Minar. There were some shadow areas, but still we get the best point density. Okay. So this is why we require multiple integration of multiple techniques. So this is an example to show you. Okay. So you can see earlier this was the situation. We were not having the complete details. Afterwards, we have the complete details. Now, once the integrated point cloud was finalized or was there, then the next step was the architectural element extraction, because we wanted to create the blueprints of our buildings. So now I will explain you how now what are architectural primitives. A primitive is anything using which by scaling and rotation of it, we can create multiple of that. Okay, so what we have done is, now we started with, okay, now I will give you an example of Quwwatul Islam Mosque. Okay, so you can see these arches. Okay, so what we did was, we found out that what was the period in which this particular structure was built. Okay, the historical period, and in that period of time, what type of arches were generally constructed. So we have gone through a lot of literature, and we found that in that particular era, these are the basic type of arches that were generated, that were created. So out of these arches, our arch resembles which of these arch? Okay, so we found out that our arch resembles the circled pointed arch, whatever means, it is a circle pointed arch. Okay, so now what we did was, you can see this is our arch, and this is the circled pointed arch which is mentioned in the literature. Okay, so we measured the dimensions of these from the literature. We found out the dimensions, what should be the ratios for this particular type of arch, and we correlated with our own arches. You can see it is fitting exactly here. Okay. So you can see these are the arches. Now these arches have been broken. So using this technique, we can virtually reconstruct these arches also. Now, for these arches, we have taken a subset of the point cloud. You can say this is the TLS point cloud subset, and on this subset, the horizontal cross section, vertical cross section at regular increments were at both the axis, horizontal and vertical axis, were carried out, were done, and the primitives were generated. You can see. Okay, so now we have this primitive which can be used for any other location. Then we have selected the shape. This was the radius. Okay, so we have this is the rectangle, means this shape is created using a rectangle and a semicircle. So we have this rectangle, fitted a rectangle and a semicircle in that, and using both of them, we have combined both of them and created the arch. Okay, so you can see, and then we have compared with the literature. Okay, what was there in the literature and what we have generated using our terrestrial laser scanner, and we found that the error percentage was around 2% only. Okay, and you means the literature was some 500 years old. Okay, so and our scans were for this date, so it is quite a good fit. Okay, similarly we have done for domes also. I'm explaining you for very simple structures, and then I will show you how it was done. So what are the most commonly constructed domes for that in that period? So you can see our dome resembles this particular dome. So we have taken the dimensions of that dome, and this for tomb of Imam Zamin, the dome resembles this dome. Okay. So similarly, we have selected the axis, the cross sections at regular intervals were generated. Then primitives were formed along each cross section, and a simplified shape was created. Okay, like this. So you can see this again, what best shape fits here. So based on all that, the dimensions were taken. Okay. So now how these primitives are used for extraction of or for digital blueprinting. So you can see here, I have shown you how the dome, how the tomb was, the shape of the tomb was created. Then you have some structure here also. So we can do certain amount of image processing and find out its primitive. Then we have, suppose if you can take any structure. Okay, suppose this structure has been taken, we have extracted the architectural element, then we have done certain image processing operations, and we have got the edited shape. Okay, similarly, suppose these are the carvings are there. Okay, so what we will do, we will not we will somehow extract one single piece of the carving. Okay, because in the historical structures, in historical buildings, there's a lot of symmetry. So if you have created one primitive, you can just you can go on copying it, and you can generate the entire structure. Okay, so if you have generated a primitive here, you can just copy, and you can create the entire line drawing. Similarly, all the line drawings for Charlie, for carving, for pillars, everything was separately extracted separately, and at the end, all of them, because they are on scale, so at the end everything was integrated, and the final blueprint was generated using the point cloud. This is the blueprint for tomb of Imam Zamin, and this blueprint has all the measurements up to millimeter level accuracy. Okay, because the terrestrial laser scanning data that we have, that is up to terrestrial laser is very accurate. Okay. Similarly, primitives were extracted and blueprints were done for Qutub Minar also and for other areas also. So this is how, suppose this is the front gate of the Qutub Minar. So suppose there are the carvings here on top. Okay, so we will extract one single carving, one single element, and try to find out the drawing of that element. Okay, and then go on replicating it. So like this, the entire Qutub Minar, or means entire complex, all the buildings of the entire complex, digital blueprinting was carried out. Okay, you can see digital blueprinting has been done for other areas also. I'm showing you this one is for St. Mary's Church in Lansdowne area in Uttarakhand. You can see these resemble any architectural drawing that you get from any architect. It has been done on various areas. I'm showing you a few of them. Now this is the thing, this is one in which the documentation has been done. Now how the same data can be used for damage detection, this also we will try to see. Now first of all, what all damages can be there in our cultural heritage. So there can be broken pattern, there can be cracks, there is can be failure of building material, out of plumb wall, discoloration, vegetative growth, vandalism. You can see the most important of these are broken pattern, cracks, and failure of building material. So we will try to focus on them. So we'll start with the missing pattern or the broken pattern. Okay, so you can see I have taken one example of from Qutub complex only. So they have done the carving of a particular pattern they have made, and you can see that few patterns are complete, whereas few of the elements of the pattern, they are not complete, or they have been broken, they are missing, something is there. So we have utilized advanced image processing methods. We have used fractal dimensions here. Now fractal is a complex mathematical formulation which exhibits self similarity at different scales. So self similarity, so that is the key thing. So now these are, all of them are self similar. So if they are self similar, so there is a parameter called as fractal dimension. So fractal dimension of one element should be same with the other element, should be same for the third element, if the element is not broken. If its structure is same, then the fractal dimension should be same. So what we have done is we have found out a complete structure. So suppose this is the completed structure, we have found calculated fractal dimension, and we tried to identify window of similar pattern. Okay, so now you can see the potential sites have been identified where the pattern is not correctly followed. Now why here? Because here there is a gap. Okay, this is completely lost. Now there is a breakage here, so this also would be coming. So once you have this, once you have identified the potential sites, you can compare the fractal dimension at each potential site, and you can detect the sites with missing pattern and virtually recreate them. Okay, similarly here also you can see this is the pattern. So what we have taken is, we have taken a template of this pattern. So this is a template of this pattern. So for the template, we have calculated fractal dimensions and tried to fit that template throughout the area. We found out the wherever the fractal dimensions are similar, it will not give me the area, whereas the other portions can be damaged areas. Okay. So once you have found that this much area is damaged, you can simply replace it with the correct area, and you can virtually reconstruct the pattern. Similarly, here also you can see, here we have taken the full flower as the template, and we are trying to find out where it is matching, where it is not matching. Okay, you can keep thresholds, how much it is, the fractal dimension is similar, and so on. Okay, it is not so that you need to have the complete pattern as a template. Template can be anything, means here you can see, to get very precise result, because out of these means this area, suppose, where exactly the damage has happened. Okay, so to identify that, we have divided our pattern into 4 areas. You can see this is, it is divided into 4 areas, and these individual areas are matched at 0 degree, 90 degree, 270 degree, and 180 degree, and we will find out exact at which location the pattern is not correct. Okay. Now over the years, because of during the renovation works, the some other material also can be used to for in these buildings. So this change of material and cracks also can be picked up by laser scanner. You can see here, this is some different material which was not the original material of the during the time of construction. So this material is coming out so nicely in the terrestrial laser scanner. Okay, here also you can see this is the material which was not there originally. Change of material is picked out by the laser scanner. Okay, you can also find out where are the cracks, where the cracks are exactly. Now suppose I have this photograph, okay, RGB photograph, and I apply some image processing techniques on this. So on any historical building, there would be lot of edges would be there. So there would be a lot of carvings also. These carvings also would come as edges. So now all these edges are not the cracks. Okay, so when we utilize or when we use the depth data from terrestrial laser scanning along with this RGB data, we will find out exact cracks, because this laser scans, they are very laser beam is very minute. It will it will go inside the crack also, and some of them will be reflected from there. So we will get some depth in that crack also. So we will be able to identify the crack. You can see when we are not using the TLS data, we are getting all the edges, but when we are using TLS data, then only the cracks have been highlighted. Suppose I have a 2-date data. Suppose some damage has happened in the area, so, and I have the original data and the damage data. So simple change detection will give me that what is the portion that has been damaged. Okay, so these are all the methods by which you can generate, you can do the damage assessment. So this again is crack detection in some other area, and this is identification of broken pattern using pre-date and post-date data, 2-date data. Then you can also carry out virtual reconstruction of this virtual reconstruction also. Now how, because there is lot of similarity in different structures. So as you can see, in on this side of the pillar, the same design was there. On the second side also same design was there. So this design was damaged. So what we can do is we can remove the damaged portion and replace it with the actual design virtually. So as we can create the the entire structure, undamaged structure virtually. So here also you can see this is an idol damaged statue. So one part was broken. So because of the symmetry, so what we did was we have taken out, this all is done virtually. From the point cloud we have taken out this much area, replicated it, mirror imaged it, and then point cloud mirroring was carried out. It was mirrored and then it was attached here. So it was the complete structure was generated. Now, how EO data can be used for damage detection? So you must be aware about the Nepal earthquake. Okay, it happened in 2015. So these are the EO images of Nepal earthquake, before the earthquake, and this is after the earthquake, you can see. And this is the ground photograph. This is Dharhara tower. The entire tower collapsed. You can see the tower is the standing tower is there in the pre-earthquake image, and after the earthquake the entire tower is collapsed. Similarly, this is again Vatsal Durga temple in Bhaktpur in Nepal. Okay, after the earthquake this entire area was damaged. Okay, so how we can use this these high resolution data set, and we can use the image processing, advanced image processing methods for doing damage detection. So there are various methods for using textures. GLCM textures are there. Okay, so we can calculate the texture of pre-image, pre-event image and post-event image. You can see this is the pre-event image and this is the post-event image. In the pre-event image, the building is standing, and you can see this edge in the building, because this roof is hut-like roof. Okay, so this is there. You are getting it in the texture also. After the earthquake, the entire building has collapsed, and that structure, that roof structure has gone, and you are not getting it in the texture image. So when you do change detection between pre-date and post-date data, you can identify which all areas are damaged. Okay, you can see this is the pre-date data and this is post-date data. So there are various image processing methods using which you can do that. Then this again is earthquake affected area in Myanmar, the archaeological site of Bagan. The pre and post event Pleiades data was used, and we have also used the multispectral and UAV images. That also I will show you. The Sulamani pagoda has been destroyed. You can see this is the damaged pagoda. The front side has is completely damaged. So this is the pre-event image, and this is the post-event image, and you can mark these how much is the damage and where exactly is the damage. You can use the GLCM texture analysis also. The same methods that we have done for Nepal earthquake, the same methods can be used for here also. Okay. Advanced image processing methods such as Gabor, fractals and variograms have also been used. Now, why is it important to use the advanced image processing methods? Because what is happening, you can see the because these are high-rise structures, so even if we are taking the satellite image, some part of it, one part of it is going into shadow areas. So whatever damage has happened in the shadow area is not being extracted using the textures method that we have used. Okay, so by using the advanced image processing methods, such as fractals. You can see fractal methods work well for shadow covered areas, and you can get the damaged in the shadow areas also. Okay. This is the result for variogram. So for variogram also, in the shadow portion also, you are getting the results. You can see. The same UAV images were also used for assessing how much damage has happened in the area. So damage and debris visibility is restricted in high resolution satellite image due to limited view direction. You can see this shadow is there, whereas in UAV you can avoid the shadow also. UAV mounted sensor, in that we can have multi-directional view, which enables clear visualization of damaged and debris area. So ultra high spatial resolution of UAV mounted sensors enables classification of finest details. Orthorectification of UAV captured data more accurate than satellite data. So this is the UAV 3D view generated using UAV data of the pagoda, and this is the ground photograph. You can see without going to the ground also you can identify each and every part of the damage. Okay, so and you can this is a point cloud. You can do classification of this point cloud and into damaged and non-damaged areas. Okay, so this is all from my